great webcam.
That could be it. What are you broadcasting at? About 1080?
I don't know. I don't know any.
108.
I don't know any numbers. It's like 56 baud.
Remember that? Remember when you had to dial up and it was said, you know what I'm talking about? It was so much fun.
Yeah, I did. I don't remember the first time I got internet at home though. I feel like I don't remember actually living with that. I remember experiencing it at like my wife's parents' place, but I think by the time we got internet at home, we had proper internet because it would have been Norway. We had ADSL. We were part of a. I seem to recall we were part of a. The company that I worked for, Statoil, had this sort of program of like high-speed internet at home. Well, not high-speed, but DSL at home.
High speed back in that day.
Yeah, so we skipped the whole modem thing.
Lucky you, man. What were you doing back in the modem days?
Italian? I thought I was going to say stallion. What do you mean? In the modem days, what was I doing?
Yeah, you were working at. You were interpreting cross sections.
No, I would have been at grad school basically. You know, so we had whatever kind of internet we had at the department, and I was busy building websites. I should look to see if the website I built is on like the Wayback Machine or something. I guess would it be? Maybe.
Could be. So I see that you're logged into our show notes here. Wait, we didn't do the intro. I forgot. Do you want to do the intro? Go ahead.
Hey everyone, welcome to show number, I don't know what, it's got to be 66, just us this week. No guests, just Graham Gansel, Matt Hall, sitting at home.
And a webcam.
And a webcam. Stay tuned for a whole heap of notes from Graham and really nothing from me, but I feel
nothing? Literally nothing or metaphorically?
Well, there's literally nothing in the show notes.
There's literally not a single character.
There's figuratively not nothing because I'm busy as ever.
So you're just gonna wing it on the show notes? That makes me nervous.
Yeah, maybe I'll type stuff in as it comes to me.
It makes me nervous.
Live show noting.
Okay, so Matt, what's first on our list of show notes today?
Well, let's cut straight to Graham, who's out in the field. I think Graham's out there in Austin, Texas, now working on GCNs and GAEs. What are these things?
I'll tell you in a second, but before we get to that, there's something on the show notes that there's something not on the show notes that I wanted to mention, which is Austin is pretty happening in terms of technology, machine learning, and deep learning. So
that's what I've heard.
I've lived in a slow part of the world now for over a decade, and it's nice to transition into a part of the world that has one, high-speed Amazon delivery, and B,
what does that mean? What does high speed mean?
Free same-day, one-day shipping.
So like 24 hours. That's not available in NOLA?
All
right. What do you have to?
Getting off on a tangent.
What kind of city do you have to be to get on that list?
Austin. So, sorry, getting back to Austin deep learning. I went to the Austin deep learning meetup last night, and it was wonderful.
I bet it was.
So, if you're in Austin and you're looking for something to do with respect to meeting people in physical space and talk about deep learning stuff, you should check out Austin Deep Learning Meetup. The talk last night was, he's typing and I'm trying to read it while I talk. The talk last night was about recurrent neural networks and their application to NLP. And it was pretty cool. So apparently the group is, this was my first one. Apparently the group is composed of some intro to machine learning people. And also I met a couple of PhD computer science deep learning specialists. So it's pretty diverse. So it was cool.
Yeah, that sounds fun. I mean, I, I mean, I've come to terms with it and everything, but I'm an hour away from the nearest conurbation of any size. There is actually a data science meetup, not a deep learning meetup, but a data science meetup in Halifax on something like the last Wednesday or the first Wednesday of the month, something like that. And it's been a bit hit and miss, but worth going to if you happen to be in Halifax. Yeah, so that's on meetup.com. Is that where people would find that?
Yes,
Uh,
indeed.
yeah,
Which
meetup.com
is
is pretty cool.
Yeah, when I first started using it, I thought it was a little hokey, but
Hmm.
it actually really is a pretty good resource. Especially if you tailor your meetups to things which have large, not just I forget what they call it on meetup.com, but participation. You can like sign up to be part of a group.
Okay.
And in this is limited experience. In my experience on Meetup, if it doesn't matter about the size of the membership of the group, it's more. It really makes a lot of sense to go into the individual past meetups they've had and see what the attendance is like.
Right.
So if you find robust ones for attendance, it's pretty awesome.
Yeah, I've been to a couple in Houston that we found just when we were there on trips. It's not often that they line up,
Mhm.
but I usually have a quick look ahead when I'm going somewhere new just to sort of see if there's something going on.
Yeah,
And yeah, we met some actually one guy who's in Software Underground, and I still email with him occasionally. We met him there. So there you
cool. Yeah, you're definitely. I can tell you from experience shipping you a Christmas present or two, you're definitely in the land of Amazon takes 2 weeks to get to you.
Yeah, yeah, it is usually getting on for a couple of weeks. It can be. I think we've had a couple this year where it's really like been very fast indeed, like 2 days. But yeah, a lot of vendors, it's either 2 weeks or it's incredibly expensive to ship.
Yeah.
So yeah, it's like you choose. And Canada gets a kind of a rough deal with a lot of American online vendors. It's just like treated sort of like the rest of the world. So it'll be sort of next day shipping, free shipping for US addresses, and then Canada's like $140.
Free 4 week shipping.
Yeah, so we kind of get a bit forgotten about. Anyway.
Anyway, over the next 4 to 9 weeks, keep an eye out for some gifts from Austin.
Oh, sweet. Yeah, I will. Thanks. That's exciting.
What's this conversation? So he literally is writing show notes as we're talking. Here's one from Chris Jackson. What is this?
Yeah, did this pass you by? Is it
It did, yeah.
Okay, well, so there was a really fun sort of thread in Twitter that it started with Chris Jackson at size_matters in Twitter, um, tweeting a picture that he said he got from a random email exchange with Professor Johnson. I don't know who that is, but I guess it's one of his colleagues at Imperial College London. And it's a really cool satellite photo of the Horton River on the Bathurst Peninsula in the Arctic, on the border, on the sort of coast of the Beaufort Sea in northern Canada. And it's really cool because this river goes kind of along this peninsula, and then at one point it clearly used to flow into the kind of lee side, as it were, of the ragged side of the peninsula, and then at some point it's broken through the other side into the sea and sort of short-circuited. But it's a pretty neat little bit of earth porn, as people say. And there was a long. It's like I see now the tweet's got like 261 likes. So it had some legs for sure, but it immediately triggered this whole kind of bit of investigative geojournalism from various people trying to unearth papers. And Chris asked a question about the elevation of the river, and people were sort of digging into digital elevation models and stuff like that. It was kind of fun, and there's some really nice other pictures in there too.
Cool. Yeah,
Mm.
this is really interesting to see the breach on the side of the peninsula.
Yeah, and it's formed a really beautiful little delta there. That's
How old is the delta?
So they figure that I'm going to get this date wrong, but I think it broke through. They've done some dating on wood and so on that was um, trapped in the delta, and I think they figured it was from 1640. Happened after 1640, but are definitely fully formed by 1826, so somewhere in there. And that part of the world's actually just really interesting for all sorts of reasons. There's crazy mud diapirs going on in the Beaufort Sea, and one of the Upper Cretaceous source rocks in the area, the Smoking Hills Formation, appropriately enough, outcrops on that peninsula and is permanently on fire. It's such a
Wow.
good source rock that it's just burning at the surface, having been lit presumably by lightning or whatever. And yeah, so those cliffs are actually just sort of bleeding smoke. I think permanently is what I read.
I'm kind of scrolling through the conversation now. Did anyone mention a latitude and longitude or anything where you can go explore
Oh,
this in 3D on Google?
yeah, that's a good question. I like lots of people certainly found it. I posted a link to a DEM Explorer. Um, there's an Earth Observatory page that gives the lat long. If you go up to the Mackenzie Delta, it's about 100 kilometers east of the Mackenzie Delta. It's not too tricky to find.
Yeah.
Just south of Banks Island.
You know, I got together with Zoltan and his wife a couple of days ago, and we were chatting about progression of sinuous channels and rivers through time.
Hmm.
And he wants to start picking away at some sort of evolutionary machine learning process
Hmm.
for, you know, sort of like regressing river, or I guess predicting river evolution or channel evolution. And at first, that seems like a very difficult problem. But he says that he has some amazing data, like many, many times per year satellite imagery and associated masking data. So like here's a 12 by, here's a whatever 1,000 by 1,000 pixel image of this sinuous channel, but then there's a corresponding 1,000 by 1,000 pixel image of like, a mask. So like only where the river exists, ones, everywhere else, zero.
Okay,
So
interesting.
I think it's possible to do something like that, just using
Yeah,
a simple recurrent neural network. Sort of just do
yeah.
like a time series forecast moving forward through time. So you have like the 1, 2 dimensions of the satellite image, and then you have the third dimension of time.
Yeah. Well, the sequence then would be the upriver patterns, or the sequence would be the time sequence, I guess.
The
It's
sequence
like,
is in time. Well, I guess I mean the sequence is 3 dimensional, but the sort of like forward predictive dimension is time, and then the I don't know what you call that geologically, but the changing in the river parameters, the actual flexing or sinuosity or whatever is expressed through those masks.
yeah, right. Yeah, I mean, it's going to be really interesting to see if Earth systems are predictable with that few parameters, right?
Yep.
I mean, he when he was on the show a few weeks ago, and it's worth checking out that show if you missed it. It's definitely worth listening to that conversation because he was talking quite a bit about modeling sinuous channels with very simple geometric parameters, right? Which suggests that yeah, maybe you can do it with purely with geometry, which I think would surprise a lot of
Fluid dynamicists.
yeah, and
Yep.
and geologists and geomorphologists who like to look at gradients and the composition of the floodplain and the upstream sediment load and all this kind of thing. Mind you, Zoltan tweeted a picture a few weeks ago, which I'll give you the link in the show notes right now. And I mean, you look at that kind of total craziness, and you wonder just how predictable something like that can even ever be, right? These systems are incredibly complex.
Well, fluid dynamics is one of the great unsolved physical phenomenon.
There's been a lot of actually related to that picture that Zoltan posted, which is a LiDAR image. There's been a lot of LiDAR sexiness on Twitter lately. Don't know if you noticed that.
I haven't noticed that.
One.
I think so. I've done a little bit of work on chaos theory years ago, and I don't understand how, just physically speaking, I don't really understand how any fluid dynamics work actually comes out correct.
Yeah.
It is mind-blowingly unstable. And any of these systems, you know, like projecting with Navier-Stokes equations, it's like, I can't believe that works.
Yeah, yeah. Did you see these images recently? There was some incredible looking simulation of turbulence around some, I think, Boeing landing gear that had apparently taken months and months to run. It was very compelling to watch. I assume none of the actual eddies are real, right? But it gets the character, the pressures, like the average pressures on the belly of the aircraft or around the landing gear and stuff, are presumably well fit to real data from pressure sensors and so on. But obviously, the actual bits of turbulence aren't predicted. And I just wonder, in a natural system where you've got something like a turbidity current, say, it's those sort of outliers that can cause an avulsion or cause the whole channel to just sort of switch in ways that don't really happen with a thing like an airplane, right? The airplane is still just the airplane. It just has to cope with what's happening to the air. But the thing with the geological system is it responds to those aberrations, if you like, or those extremes. In fact, it's the extremes that cause the sort of non-linear and unpredictable behavior. Like it, do you know what I mean?
Those aberrations exist in other physical systems as well. I mean, in the case of the airplane, aberrations in the physical system could include things like a bird runs into your fuselage and there's a slight dent, or there's a piece of hail in the air that passes through that makes a huge difference in the turbidity current surrounding the solid object.
Yeah, right. I just feel like on the whole, it seems like you need to just know the average behavior, well, not average, but the sort of maximal behavior so that you can design to it, whereas the natural system reacts to it. It's almost like if the aeroplane was like changing shape because of the turbulence around it. So, well, I guess it does, right? On some level, yeah. It's just that becomes a design parameter. It's a thing that's happening around you, whereas in a geological system, it's the thing that you're trying to predict.
I think we're just talking about different time scales.
Yeah, right. Maybe at a given spatial scale and time scale, if it's big enough, you can predict its behavior. You might just not get every meander right.
Now we're fully into the realm of conjecture because neither of us is a fluid dynamics expert.
Anyway, I can't find that video, so it's kind of moot.
What was next? GCNs and GAEs. Before we do, well, okay, we'll do it real quick.
Before again, you're just gonna.
We'll do it. We'll do it real quick, okay? So, graph convolutional network. I think I've already mentioned this on the show, but I'm going to do it again as I've been playing a lot with these things. Information spaces don't exist on they don't even exist in physical geometry. So that is to say that many systems, especially sort of like relational systems, information systems, do not exist on Riemann manifolds. That's a problem for machine learning, although we'll get there. That's a problem for machine learning implementations, current implementations of, say, neural networks, because some of the most successful architectures in the machine learning space depend on a Euclidean relationship between spatial dimensions. So, stepping back to a higher level, if you analyze an image with anything, like a standard filtering algorithm or a convolutional neural network, the kernels which operate on the data assume that pixel at location 1, 1 is next to pixel at location 2, 1, and also pixel at location 1, 2. So images in traditional convolutional neural networks exist in the Cartesian space, Euclidean geometry. You move left, right, up, down, and it's smooth, which is important. So there are no strange loopbacks inside of image dimensions. There's no twisting of images. There are no discontinuities in images, sections where the dimensions stop. So convolutional neural networks work really, really well. Not the case on information networks or so-called graphs. In that case, in the case of graph theory, your space, your sort of geometry of your information space, can have these weird discontinuities where the space abruptly ends and starts again. And it can have recurrent dimensionality where sort of things connect to themselves in strange ways. Not to mention that.
So hang on, and just so I make sure I'm clear. So in a sort of Euclidean space, in a bunch of pixels, it's just a regular grid.
Yes.
So everything has, it's very easy to tell what everybody's neighbors are, and everybody has the same kind of neighbors. It's like a plan of Manhattan. Well, not only Manhattan, but Portland, Oregon. Happens to have square grids. Whereas in a graph, like a network style of graph, the concept of neighborhood is a bit more flexible. Is that what you're saying? Things can be connected to other things which are far away, some things which are very close. They can be connected to themselves. They can have many neighbors. They can have few neighbors. They can have no neighbors.
Yeah.
So it's a different kind of space. So my question is, why would you try to use convolution on something that doesn't look at all like an image type of a thing? How could that possibly work?
My question back to you is, why would you attempt to use convolution at all? I mean, this is a educational exercise. So why did people invent? Why did the Fouriers of the world invent convolution in the first place? And then additionally, like, why did humans start using convolutional neural networks as opposed to just
So I mean,
networks?
I feel like it's just sort of neighborhood statistics, right? It's a way to tell something general, but not too general, about a place in something, whether it's a position on a one-dimensional line or a position in a 2D thing or a 3D thing. It's neighborhood statistics.
It's a way to build up abstract representations of information contained in that space.
Yeah, cool.
So the answer to your question is the same thing. If you are forced to look at individual nodes in a graph, or individual disparate pieces of information inside of an information space, you can never learn. I actually don't know that if this is true, but I'll make the claim that you can never learn as much not using those spatial relationships as you can using them, which is why you want convolution.
Okay.
Be interesting to see that as a proof.
So
Not sure
because
it's done.
you're saying essentially that there's always extra information to be gained from looking at the neighborhood of something,
Yes,
right?
always.
Yeah, that makes sense. That's the basis for statistics, like these sort of recursive type statistics like PageRank and eigencentrality that you get in graph theory, right?
Yes,
Where it's like, I can tell more about this vertex because I know something about the things it's connected to.
that's
Cool,
right.
cool. Okay, well, that seems valid. I
Okay.
approve of this line of reasoning.
Okay. So there are a couple of tricks you can play if you want to consider links and vertices that are adjacent to, in some form, the piece of information that you are currently poised on.
Considering, yeah.
So one of those ways, the light duty way, is to do some sort of node vertex embedding. So you essentially collapse information onto a lower dimensional space, and then you perform your analysis with conventional tools. So you just mentioned eigenvalue decomposition.
Okay. Okay.
Yeah. Did I lose you? No?
Uh, I don't really understand how gives you access to the usual convolutional approach.
Okay. So what if we did? What if we took non-image? Let's say we wanted to build an apples versus oranges classifier.
Okay, I need one of those.
And we wanted to do this um, in a variety of ways, but we have some intuition that using spatial relationships is going to improve our accuracy. So if we have 3 dimensions in our input feature vector, so let's say like color, texture, squishiness,
Okay.
you can't use that feature vector does not exist on a 2-dimensional plane necessarily because it has 3 dimensions. So we could play tricks about dimension. We could play tricks on the input vector to collapse that information into 2-dimensional space,
Yeah.
assuming that's something we wanted to do.
Yeah.
One of those tricks would be we take the color attribute and we leave it alone. And then we take the squishiness attribute and the texture attribute and we multiply them. So
Okay.
we're
Sure.
left with 2 features. Boop, 2-dimensional space.
Mm-hmm.
So that's one type of feature embedding.
No. Okay. No, okay. So, but I guess I don't. The bit I don't understand is how, when you've got that lower dimension representation, how that helps you with the application of convolution to this problem. See what I'm saying?
Okay, so we're talking about 2D convolution in this case because we already have all these open source libraries that do 2D convolutional neural networks very well. That's the only motivation.
Yeah. Okay. But it seems like you're still stuck in this weird non-regular grid kind of universe, right?
Right. So if we take information from the network, from the graph, and we perform some sort of transformation, we can embed all of the information into as whatever number of dimensions we want. Now we lose some information by doing that, and we potentially corrupt relationships between features by doing that. So we could, if we have this sort of weird contorted information space, by collapsing it into a lower x dimensional space, we do lose information, or we at least stand to lose information.
Yeah.
But if we do that, again, we can use our standard tools to analyze. the space.
Okay.
I don't know if I maybe missed.
Yeah, I just feel like the thing that you end up with after the embedding still looks, it doesn't look like an image.
Well, if you collapse it to two-dimensional space, it will look like a something in 2D.
Oh, I see. You're just going to treat that as a bunch of pixels, essentially.
Sure.
Oh, okay. So, but then you lose the edges, don't you? I guess they don't have edges in that embedding.
So if you think about an adjacency matrix, you know, so an adjacency
Yeah.
matrix is the relationship is the link relationship between nodes.
Hmm.
That is something like an image.
Okay. Okay. Yeah. Okay. So that's the thing that you've reduced to 2 dimensions.
That exists in two dimensions already if you wanted to, because you
Yeah.
can
Right.
just organize your nodes in transpose order.
Yeah. Yeah.
The thing that
So why
so
not just, okay.
yeah, so the answer is when you look at this adjacency matrix in its natural in its raw form, you are left with a system which is not classifiable by standard CNNs
No,
because
it's
the
not organized, right?
that's right.
There's no meaning to the spatial arrangement,
That's right.
right?
So
But the
the
embedding has meaning.
yes, in some it's like doing some strange transformation like a PCA, like a principal component analysis.
Sure. So
We
you
don't
just
really know
treat,
what the dimensions are.
so you sort of just treat that as a sparse matrix, basically? Is
Yep.
that okay? So it's just full of zeros and ones,
Well,
like,
it doesn't have to be ones. If it's a weighted graph or there's no edge properties or something, each one of the
okay.
pixels has weight.
Yeah, okay. Cool. Interesting.
So that's node embedding. So that's the light duty version. The heavy duty
Okay.
version is actually building convolutional kernels which operate on generalized spaces,
I see.
non-Euclidean spaces. So that is the GCN mentioned in the notes.
Okay, so that's generalized convolutional
Graph convolutional network.
graph convolutional network. Okay.
All right, so if we think about just man, this was supposed to be a quick explanation. So we'll do
No, it's interesting.
5 minutes more. So if you think about the standard one-dimensional convolutional operator, it's a pretty simple thing. You basically take two functions or pieces of information and you slide them past each other, right?
Yeah.
Summing as you go along.
You're supposed to reverse one first, but
Sure.
it seems like people don't usually do that.
Well, that would be called correlation if you didn't do
Right.
that. Okay, so that's a standard 1D Euclidean convolutional operator. But what if, so again, if your sort of x-axis or whatever, your time axis or your progression axis in your signal is non-linear with respect to Euclidean space, you can't perform that same analysis. So you
Right.
have to design the kernel, the filter operation to operate on that sort of nonlinear space. So that's what we're talking about doing. I mean, that's what people are doing in the GCN world.
Right.
And it's awesome. So anyway, the other node in there is GAE, which is Graph Auto Encoder. So I'm using graph convolutional networks to do subgraph and node classification and prediction. And I'm using GAE's graph autoencoders to do link or edge or whatever prediction in those information spaces.
I see. Fascinating.
I think
Very
so.
cool.
So there you go. There's your not so brief introduction to GCNs.
Yeah.
Next bullet
Well,
point.
That's got me thinking. Very cool. Well, please come to the hackathon at AAPG in May to think and talk about and maybe do some of that stuff on stratigraphy.
Okay, deal.
We'll find a data set, an appropriate data set.
Hey, let's tack here and talk about the amazing Nvidia V100.
Oh yeah, you got your little mitts on one of those, have you?
Have you used one yet?
No.
They're everything they're supposed to be.
Okay.
They're amazing. I just have AWS instance running or whatever. And oh my God, it is insane. If you use, so they have this, I don't understand anything about computers, but they have this TPU architecture, tensor
Yeah.
processing unit. And they claim that these V100s can get up to 125 teraflops. So you have to use like half precision numbers to do these operations, but it is crazy. I mean, they absolutely tear through training. It's wonderful.
Oh, really? Wow, that's cool.
Mm-hmm.
Yeah, so that's Nvidia's. It's like a software-defined thing, isn't it? These TPUs, they're sort of.
No idea.
I don't think they call them TPUs, do they? I thought that was a Google thing.
I think they do.
Because certainly they seem to have these. I don't know. When I read about it, I was like, oh, this sounds more like a Me Too thing from Nvidia, while they actually build some hardware technology around it. Because Google's TPU is an actual, it's a chip, which actually they
Tensor
just
cores, yeah, that's what they
announced.
call them. Whatever.
Yeah, okay. Google just announced the TPU V2 will be going to the cloud like as soon as it's released, I think. And that's interesting because the current TPUs don't do training; they only do inference. The training and inference, and they'll be available on Google Cloud at some point. So I was looking forward to having a play with those. But yeah, I should give these or get Diego to give these V100s a try too. We're not actually doing any deep learning right now. We're sort of in a bit of a hiatus, doing some other stuff. But when we get back to it, maybe we'll give it a go. Yeah, I was reading about the concept of the TPU is it has to be good at slightly different things from a GPU, I guess, from what we normally might use. And the two things were, one of them is obvious, really, which is matrix multiplication. So it has to be good at this particular type of operation. But the other thing I hadn't really thought about, but I like the sound of it, and I haven't given it a huge amount of thought or anything. But this was Jeff Dean talking about this. So, I mean, the guy knows what he's talking about. He built most of Google's infrastructure, I think. And the way he expressed it was just that, like, look, we don't need all this precision. Like when we're doing deep learning, when we're learning these weights, actually, we don't need, 64-bit floats. We can get away with much, much less precision. And I'd never really thought about that before, but I love that concept. I'd love to see more of that kind of thinking come to seismic processing, like how can we make this faster by actually only caring about a smaller set of things. Yeah. So I like that trend.
Indeed. It's elegant. Elegant
Yeah.
solution.
And then the other one, which I also know nothing about, and we should find someone to come on the show and explain it to us, is the FPGA stuff and the sort of, programmable hardware, essentially, where people are actually kind of building the network into the chip so that it's actually a physical neural net, essentially.
My
It's
goodness.
my naive understanding of it.
You know who we should get on the show to talk to us about this? My dad.
Yeah.
Yeah, he's a software. He's an embedded systems expert. He has been dealing with FPGAs since they were conceived of.
Oh, right. Yeah, let's do it. That sounds awesome. How did you come up with him?
That's right.
I bet you're seeing him this holiday season, aren't you?
No, because he's going to be in Virginia and I'm going to be in New Orleans.
Oh, well, let's track him down.
Yeah, I'm sure we can find him somewhere.
I bet you've got his number.
Hey, so I wanted to mention a thing that I would like people to start touching on at the Geo hackathons. So
okay, cool.
The thing that I'm doing right now with this GCN that we just talked about is a two-part talk. And the second part of the talk is to discuss the relationship of bias in humans to bias in models.
Hmm.
So we're trying to quantify that. And it would be really interesting to see. You and I have talked extensively on the show about uncertainty in subsurface experiments. It would be interesting to see if we can try to quantify some of the uncertainty in the modern machine learning methodologies in geoscience. My particular topic is based on a credit worthiness prediction, and it is an analysis, quantitative analysis of how biased machine learning models are. One particular machine learning model is against women being approved, just disproportionately fewer times than men for small business loans. So keep that on your radar. And as we get closer to this next hackathon, it would be really neat to challenge some people to discuss uncertainty. Because I think even though uncertainty is such a sort of elusive beast in the geoscience world, it is conceivable that by using these discrete pieces of analysis, like these machine learning pieces of analysis, we can start to get a handle on individual uncertainties in the full workflow.
Yeah, well, yeah, sure. I mean, I feel like a big piece of it is this sort of cultural hang up and inability of other pieces of the workflow to deal. I mean, we've had access to pretty good quantitative estimates of uncertainty since we started doing stochastic simulation, and it's still not standard to pay much attention to those distributions and what they're telling us about the predictability of a system. So I mean, do you know what I mean? Like, I feel like, yeah, machine learning and neural networks and things give us another way to express those distributions, and maybe they're more reliable. I don't know, but nobody cares.
Okay, so maybe my point is that we have these whippersnappers using these new methodologies, and hopefully we can convince them to look at uncertainty distributions.
Yeah. I mean, I don't know what it takes. I've speculated before, probably on this show, whether the problem is that when you get bottlenecks in tools, and that bottleneck might be technology, like, oh, the finance person uses a spreadsheet and they only have one box for that number, but it might be quite a sort of irrelevant seeming bottleneck, like the main way of communicating with the rest of the team is through email. And so it tends to be things written in sentences. And do you know what I mean? Like, there's just a horrible data transaction happening that causes most of the richness of your data to disappear. So
dimensionality reduction.
Yeah, basically the dimensionality reduction of email. Yeah, I think it's fascinating how resistant we've been to quantitative treatments of uncertainty.
Well, at least in industrial practice, I mean, there's a
fair enough. No, I would say in academic literature as well.
No. Sorry, my point. Yeah. So in industrial practice, maybe analysis of those uncertainties is actively ignored.
Oh yeah, okay, yeah, sure. Well, yeah, but weirdly, you'd think there, if anywhere, there was a vested interest in getting a better handle on it, and yet there isn't. Even if we don't use it for prediction in the kind of forward sense, we don't use it in the. There's no back propagation
correcting
in exploration.
Yeah,
it's completely missing from our workflow, and at least, I mean, I've always sort of assumed that, well, Exxon must do stuff like that, Shell must do stuff like that, but I don't know. There's not a huge amount of evidence for that. But
this is the holiday episode.
Oh yeah.
And we haven't talked about
Merry Christmas.
Our holiday gift lists yet. So we need to do that, and in the show notes, you need to remind me to point out to our listeners. Skip ahead to minute XYZ to get to the good stuff.
Get to the good stuff. Yeah, skip ahead of this nonsense.
So you released your Christmas wish list a
I
while
did.
ago. Yeah.
Yeah,
What was on
yeah.
it?
It was
You go first.
wrote, and I'm embarrassed to say that was 2 weeks ago. I I got into, maybe we'll get a chance to talk about it. Probably won't, but I got twisted off on the old the old chestnut of rainbow color maps and haven't been able to finish that blog post basically ever since. It just won't go away. That whole, like, it's like a meme, and it won't die because every time it comes up, some really smart, considerate people go, actually, I quite like the rainbow color map. And it's like, ah. Anyway, yeah. So gifts, I did. So the gift list is up. No one has commented on my awesome title, the punniest title I've
Oh, that
ever
was,
written.
and there was another pun related
For
to
a,
that inside the post, right?
there was, yeah.
Yeah.
And no, I don't know. I mean, I don't
What's the
know. I
title? What's the
noticed
title
it.
of the post?
The post of Christmas present. It's just, it's so good it hurts. And I haven't had a single remark. So
Well, has anyone?
I'll give
It
up.
looks like some people have. No one even remarked on the gift list. Some of these are reused, man. This is the problem. You got to come up with new stuff every year to entertain the readers.
No, like
Yeah,
what?
yeah. The keychain, uh, pull apart geologic model thingy.
Did I do that before?
Yeah.
Oh, I'm so lame. On, right?
I thought there was another one in there too, but no. Okay. Well,
Where did
anyway,
where did I use that? Are you
it came up somewhere. I go back to
yeah,
your
yeah,
last
yeah.
year's.
No. It would be from earlier in the year because John Lehman was the uh, expert advisor on that
Oh,
little.
I apologize. I thought this was on your last year's Christmas list.
I I resemble that remark. Um, I, I'm not saying it couldn't happen, but basically, I start collecting gifts for the year as soon. In fact, my list for next year has already got 3 things on it because there's stuff that I missed for this year. So I mean, it is old, up to a year old.
Can we talk about your Christmas list already? What's on it? Our listeners want to know.
There's some cool stuff on it. There's a Lego seismometer. The new Raspberry Shake seismometers are out, or yeah, I think, or coming out. Anyway, the Raspberry Shakes are awesome. As you know, I really like globes. So I linked to a really nice moon globe. There's also, and I got some of these myself, an outfit called the Little Planet Factory that 3D print very beautiful little planets at all sorts of different scales. They're really cool. They actually have stopped selling them, but their models are on Shapeways, shapeways.com. So you can actually just order their models directly from Shapeways.
What's the largest one you can get? Planet 1-to-1 scale?
I think so, yeah. Maybe they do a 1-to-1 of a little meteorite. There's my favorite thing, and Steve Purvis tweeted this out as well, was it's a life-size actual model of Earth. It's 8 mm in diameter. And I'm just looking at the name of this particular type of model because it's not coming to me. But it's the size that Earth would have to be if Earth was a black hole. Okay.
Oh yeah.
Makes sense. It's called the Schwarzschild radius.
Yes, I remember.
So you can buy this Schwarzschild radius Earth. It's, I think, 8.869 millimeters in diameter.
That's
and
much larger than I would have thought, actually.
Have that on your desk. It's pretty cool. What else is on my list? I mean, it's all good stuff. Some really great books. I tried to put some new books on there that came out kind of after November. All the latest Earth science books, including ours, of course. A couple of them look really great, actually. Reading the Rocks. It's about Victorian geologists.
I love the puzzle, the jigsaw puzzle.
That puzzle's amazing. Yeah, it's like an algorithmically generated puzzle that looks like agate. Not only is the agate pattern algorithmically generated and semi-random, but the puzzle piece shapes themselves are algorithmically generated by a separate algorithm. So it's very geeky indeed.
And if you're into jigsaw puzzles, this looks like probably one of the hardest.
It does look really hard, and the piece shapes are pretty wild. Like they are not your regular. They almost look like sort of acicular crystals. They're pretty neat. And then if you want your house to look like a kind of Bond villain lair, you can get these crazy massive, well, it's wallpaper basically that looks like kind of mineral thin sections and a transmitted light, reflected light. And some of them, you know, it's just big botryoidal habits and things on your walls. They look kind of cool.
Yeah.
Yeah. You know, you said you were going to do one too. Have you done that?
Yeah, I did a mini list. It's in the show notes.
Okay.
So Matt does his geoscience Christmas gift list every year. So I said, well, let me try to do a data science gift list this year. So there's a couple things. One I stole from Matt, which is the Amazon Deep Lens, which is pretty cool. It hasn't come out yet, but it's going to, and you can check that out. There's a link on the notes. So gift cards, I picked a couple things which are actually useful to people in the data science community. One is doing the online courses if you're sort of an intro to data science or intro to machine learning person. There's Udemy, there's Khan Academy, there's Coursera. So if you want to do one of those courses and of course receive credit for it, you have to pay. So you could get your friends and family Udemy courses gift cards. The biggest one, the one that I always want, is Amazon Web Services gift cards, because you can actually, so just regular Amazon gift cards, you can pay your AWS bill with those cards, which is pretty cool. So guess what I will be doing with all my Amazon gift cards that I don't receive this Christmas. The external GPU thing, I don't have a link on here for this, but this is such a cool idea. So you were experimenting with this year, and it's worked out really well for you, right?
Yeah, I'm very happy.
So I couldn't find a link with a complete build list, buy list, press this button to check out site. Have you ever seen something like that?
Well, for the kind of, I mean, I just get these kind of fully engineered aftermarket plug and play things. Are you talking about like building one yourself?
Both things.
Yeah. I mean, the big ones, the big one for Mac users is the Bison box. And the more generic one is the Akitio node, or the Akitio node 3, I guess, is the USB 3. And basically, yeah, you buy the box, which has the power unit and the interface, and you buy a GPU kind of off the shelf, as it were. And it'll fit pretty much any GPU, I think. These things, they're pretty decent sized boxes.
What I wanted, yeah. I was trying to just find a thing that was like one page with the housing, the power supply, and the card and everything all together that you could just buy all at once. Couldn't find it.
Yeah, Bison box will be the not cheapest, actually, probably the most expensive, but the most self-contained package.
Yeah.
But and it's not so much that you couldn't use the Bison box with a non-Mac. I think it's just that they only ship like the little software package, you know, that they interface with for the Mac. So in other words, if you were putting it on Linux box, you'd be kind of on your own with getting it to recognize the graphics card and all that kind of stuff.
So this is related to my next bullet point here on the data science gift list, which includes hardware hacking, peripherals and stuff. So many of us in the Nerdist community like to build our own little gizmos. So maybe you already have a computer that can receive a nice GPU, buy someone a GPU. But also this includes the Raspberry Pi extensions. So it's cool to have a Raspberry Pi, but it's also really cool to have like a little thing you can fiddle with. So there's all these little kits where you can build little Raspberry Pi laptops and computers. Some of them are pretty well oriented towards kids too, so, which I think is awesome. So there's one I have a link on here called Kano Kits or Kano Kits. I don't know how to pronounce it. And it is sort of like learn to build a computer and learn to code all using this thing. It's awesome. Cool. And the last two are actually productivity tools for the data science or any sort of techie workspace. One is Bluetooth headphones. Man, I'm not wearing them right now, and I wish I was because I'm tethered to my computer and I can only move my head so far away. But I have Bluetooth headphones. I've worn them for a couple of years now, and they are seriously life-changing, especially if you wear headphones a lot while you're working.
Oh, really? See,
there's a list of they're the best.
I've had a couple of Bluetooth speakers, but it's like not recently, and they was just so annoying for, you know, just
for what?
Dropping the signal or not connecting properly and all this kind of stuff. I was just like, this is a waste of time. But you're saying these are pretty good? They're pretty reliable?
I wear these at least every day. These are,
okay,
I don't know, Bose something. They're amazing. These are earbuds. But then at my office, I actually have a pair of like noise canceling over ear headphones, and they are awesome. Get them for your for your friends and family. And then the last thing on the list, which is kind of cheesy, but is serious. So Xpero has whiteboards all over the place. And man, I forgot about how much I love to stand at a board and like think it out and brainstorm with other people. It's a big deal. And I hadn't had that for many years. Like between the time I finished school and the time I had to pay for all this junk in my office, and never bought any whiteboards. I should have. So get yourself some whiteboards. There's just a link on the list to the Amazon thing, and they have them. I mean, you can get standalones, you can get hang on your walls, you can get like roll them out in sheets, paint them on, anything you can think of.
Yeah, whiteboard paint. So I haven't actually bought any yet, but I've done a bit of research around it, and the thing I learned was don't skimp. Because it's worth getting decent whiteboard paint. Apparently, some of the other stuff just like it stains. You never quite rub off the ink, or it's a bit rough or whatever. So anyway, I really want some for our co-working space, but the good stuff is not cheap.
How much are we talking?
It's like a few $100 kind of thing
for
to
what?
do a wall. To do a wall.
Okay.
Yeah.
Not a gallon.
Yeah, it's not like a tin of paint, that's for sure.
I guess
I just added something to your list.
The Movidius Neural Compute Stick.
Yes. So this is one of Intel's projects, and it's a pretty cute little USB stick. It's made out of aluminium, so it feels kind of nice. And basically, you can sort of compile models from platforms like TensorFlow and upload them to it, and then it'll do inference only. So it's a way to make a portable model that will do pretty fast inference once it's set up. Yeah, and they're $79, so it's not particularly expensive. But if you're looking at plugging a network trained model into something like a Raspberry Pi, or you want to give it to someone else, or a cool thing to give to clients maybe, then it's kind of a neat little gimmick. It's sort of a developer toolkit thing, but I've got some for a future hackathon prize.
Cool.
You can expect to see those pop up in Salt Lake City. If you want one, come and be awesome at the hackathon.
Awesome.
I'll give you one.
Well, that's it for us. That's all the time we have.
Oh, I was just getting into that as well. I'm kidding. Oh man, I'm so sleepy.
Wrap it up here on this show. Well, we'll see our audience when. It's going to be a while.
Could be a couple of weeks.
Could be a couple weeks. So hang in there. We'll still be here, and we look forward to seeing you then on Undersampled Radio. Bye.
Bye, everyone.